Welcome to the deep dive. Today, we are strapping in for, well, a really focused tour of foundational electrical theory.
Yeah, it's foundational but crucial.
We're not just covering basics, we're going after the essential stuff you need to know to safely, understand and test industrial circuits.
Exactly. Our mission today is pretty laser focused. We want to equip you with the electrical fluency, let's call it, to interpret readings, understand basic DC circuits.
Because you can't really tackle the complex stuff, like rectifiers, without this solid base.
You absolutely can't. It all comes down to the building blocks: voltage, current, those key passive components, and crucially, how to measure things properly.
Okay, so let's start right at ground zero, the two big families, DC and AC, direct current. That's often seen as the simpler one, yeah.
In a way, yes. DC flows in, well, one direction. The polarity doesn't flip.
Like a battery.
Like a battery is the perfect example of constant DC. But, and this is important, DC can also be pulsating. Think about the raw output from a basic DC generator or even a simple rectifier. It pulses up and down, but it never actually reverses direction. That's the key.
Got it. Which brings us to AC, alternating current, the power that, comes into our homes and factories.
Right. AC is inherently dynamic. It's constantly reversing direction, reversing polarity. We usually picture it as that classic sine wave.
Generated by rotating machinery, like alternators.
Exactly.
Now, here's where I think a lot of people, even experienced techs sometimes, get tripped up. Interpreting the numbers on the meter. When you measure DC, it's straightforward, right? The meter gives you the average.
Yep, your DC voltmeter automatically calculates the average DC value. Simple enough. Even for pulsating DC, it gives you that average between the peaks and valleys.
But AC is different. We have several values floating around. Peak, RMS.
That's the crux of AC measurement, really. You've got the peak value, sometimes called maximum, VP, or IP2. That's the highest point the wave hits, positive or negative.
And peak to peak, it's just double that.
Double the peak, yeah, from the positive peak to the negative peak.
Okay, but if I'm looking at equipment specs, say a 480-volt AC motor, that number isn't the peak, is it? It's usually the RMS value. Why is RMS the root mean square? Why is that the gold standard?
Because RMS tells you about the work being done. It's all about the heating effect. It's the practical value.
Heating effect.
Think of it this way. 120 volts RMS AC going into a simple electric heater produces the exact same amount of heat as 120 volts constant DC. That makes it the useful equivalent value for comparing power.
Okay, that clicks. RMS is the DC equivalent for getting stuff done, basically.
You got it. And critically, unless someone specifically says otherwise, any AC voltage or current value you see on a nameplate, a manual, whatever, it's always RMS. Always.
And there's that conversion factor we need to know.
Yep. RMS is the peak value times 0.707, so IRMS times 0.7071. That's one to definitely commit to memory. Helps for quick checks.
Good tip. Okay, moving on to the language of circuits. We need some shorthand. Time first. Period and frequency.
They're inversely related. If you know the frequency F, like 60 hertz here in North America.
Then you instantly know the period T, the time for one full cycle.
Exactly. T equals a 4/0 failure. So for 60 hertz, that's 1 divided by 60, which is about 16.7 milliseconds. Knowing that cycle time is really useful when you're troubleshooting things that happen fast.
And for figuring out potential differences in complex circuits, we use double subscript notation. Why is VBC not the same as VCBA?
It's all about your reference point. VBC means the voltage at point B with respect to point C.
So the second letter is the 0 point for that measurement.
Precisely. If you flip it to VCB, you're measuring C with respect to B, so the value will have the opposite sign. It's just a very precise way to talk about voltage differences.
Okay. And one last calculation shortcut, especially handy in series circuits. The voltage divider rule.
Oh yeah, this saves a lot of messing around with Ohm's law sometimes. It basically says that in a series circuit, the total voltage splits up or divides across the resistors in proportion to their resistance values.
So the bigger the resistor, the bigger its share of the voltage drop.
Exactly. The formula, VXRT times ES, lets you calculate the voltage across any single resistor, just by knowing its resistance, the total resistance, and the total applied voltage, E.
So if I needed, say, exactly 5 volts for a sensor from a 24-volt supply, I could use this rule to figure out the right resistor values to drop the other 19 volts.
That's a perfect practical application. Designing voltage dividers or just quickly checking if the voltages you're measuring in a circuit make sense.
Perfect. Okay, we've got the language down. Let's shift gears and meet the main players. The passive components, R, C, and L.
Right. Resistors, capacitors, and inductors. These three really dictate most of the electrical behavior we see.
Starting with the resistor R. Seems simple. It just opposes current flow. We see fixed ones, variable ones like potentiometers.
Yep, pots, trimmers, rheostats for higher power.
But beyond the ohms value, what's critical for a technician to check?
The power rating? In watts. Always. You've got the resistance value, sure, and the tolerance, maybe plus or minus 5%. But if you ignore the power rating and push too much current through it, it'll overheat and burn out.
And the power rating usually relates to physical size, right? Bigger resistor, more watts.
Generally, yes. Those tiny little carbon film resistors might only handle a quarter watt, while a big ceramic wire-wound resistor could handle hundreds of watts. Size matters for heat dissipation.
And reading them, besides the color code bands, there's that KRM method. How does that work? Say, 2K2 pin?
It's actually pretty neat, common in industrial stuff. The letter R, K, or M just takes the place of the decimal point.
Ah, so 3R33 is 3.3 ohms.
Exactly. And 2K22 is 2.2 kilohms. 1M55s would be 1.5 megohms. It avoids potential confusion with smudged decimal points.
Clever. And one last thing on resistors and AC circuits. Phase relationship.
Simple. In a purely resistive AC circuit, the voltage and the current are perfectly in phase. They rise and fall together.
Okay, now for the components that mess with that phase relationship. First up, the capacitor, C. It stores charge.
It stores charge, yes, but functionally, think of it as opposing a change in voltage. That's its key dynamic behavior.
And it's basically just two conductive plates separated by an insulator, the dielectric.
Right. Capacitance, measured in farads, depends on the plate area, the distance between them, and what that dielectric material is made of.
We see different types: paper, ceramic, mica. But then there are the polarized ones, like electrolytics and tantalums. And you flagged a major danger here.
Huge danger. You never, ever connect a polarized capacitor like an electrolytic to an AC supply. Or backwards in a DC circuit, for that matter.
Why? What happens?
Remember, AC reverses polarity constantly. These capacitors have a very thin chemical oxide layer that acts as the dielectric, and it's formed to work with voltage in only one direction. If you apply reverse voltage, like AC does half the time, you essentially destroy that dielectric layer very quickly.
And the result is?
Usually pretty dramatic. Internal gas buildup, pressure. It can bulge, vent, or even explode. Seriously bad news.
Okay, critical safety point noted. In DC circuits, we talk about the RC time constant. T equals R times C.
Right, that tells you how fast the capacitor charges or discharges through a resistor. The rule of thumb is it takes about 5 time constants, 5T, to be considered fully charged or discharged.
And in AC circuits, how does the capacitor affect phase?
The voltage across the capacitor always lags behind the current through it, or you could say the current leads the voltage. This is why capacitors seem to block DC but pass AC.
Makes sense. All right, last of the big three, the inductor, L, often called a choke. If C opposes voltage change, L opposes.
A change in current. It does this by generating a voltage that opposes the change, a counter EMF, or CEMF.
It's basically just a coil of wire, right? Measured in henries.
More turns, more inductance. Also depends on the core material, coil shape, etc. In AC, the current flowing through an inductor always lags behind the voltage across it, opposite of capacitor.
So it chokes off sudden current increases.
It does. But it also fights against sudden current decreases, and that's where its own safety hazard comes in.
Ah, right. What happens if you suddenly open a switch in a circuit with a big inductor, like a relay coil or a motor winding?
Because the inductor wants to keep the current flowing, it resists that sudden drop to zero. To do that, it converts its stored magnetic energy into a potentially massive voltage spike, the CEMF spike, right across the opening contacts of the switch.
Zap. Can damage the switch or other components.
Easily. This is a really important effect. Think about current transformers, CTs. They're highly inductive.
And the rule is you never open the secondary circuit of a CT while the primary has current, right? You have to short the secondary terminals first.
Absolutely mandatory. If you open that secondary circuit under load, you're interrupting the current path for the inductor. It will generate an extremely high, very dangerous voltage spike across those open terminals trying to keep the current flowing. It can destroy the CT and be a serious shock hazard.
That CEMF is powerful stuff. Okay, we've met the players, but theory is one thing, verifying it is another. Let's talk tools and testing.
Good idea. And the first big distinction is static versus dynamic. Your standard multimeter, voltmeter, ammeter, ohmmeter gives you static readings, a snapshot in time.
Whereas the oscilloscope, That gives you the movie.
Exactly. The scope shows you dynamic values, voltage, plotted against time. That's essential for seeing waveforms, ripple, noise, things a multimeter just averages out.
Let's cover the multimeter basics first, though. Using an ohmmeter, common mistake.
Trying to measure resistance while the component is still connected in the circuit. You must isolate it, or at least ensure there are no parallel paths. Otherwise, you're measuring the resistance of the whole network, not just the part you want.
And interpreting the reading, ALL means
Open loop, or over limit, basically infinite resistance and open circuit.
and 0 ohms.
A short circuit, or at least a very, very low resistance path.
Okay, ammeters. The clamp-on type is super convenient for AC, especially higher currents, senses the magnetic field.
Yep, no need to break the circuit. But they're often not very accurate for low currents, say below 100 milliamps or so.
So if you need to measure small DC currents, like in control circuits,
Then you have to use a series ammeter. You physically open the circuit and insert the meter in series so all the current flows through it.
which leads us to the big safety rule. Never, ever connect an ammeter in parallel, like you would a voltmeter.
Never. An ammeter is designed to have almost zero internal resistance. Putting it across a voltage source or parallel to a component is basically creating a direct short circuit.
Bang, you'll blow the fuse in the meter, maybe damage the circuit, possibly worse.
Absolutely. Voltmeters in parallel, ammeters in series, period. Gotta drill that in.
Got it. Now the oscilloscope, saying voltage versus time.
It's such a powerful tool. You have the vertical controls volts per division to set the voltage scale.
And the horizontal controls time base, seconds per division to set the time scale.
Right. And the trigger control, which is key for stabilizing repetitive waveforms so they don't just scroll randomly across the screen. It lets you see the shape, measure frequency, amplitude, look for distortion.
And one really cool thing is seeing AC and DC together, right? Like ripple on a DC supply.
Yeah, you might see a sine wave that isn't centered around 0 volts, but maybe it's riding on top of, say, a positive 5-volt DC level. The scope shows you both that steady DC offset and the AC component superimposed on it. A multimeter would just give you an average DC reading and miss the ripple entirely.
Very useful.
Yeah.
And circling back to safety one more time, large capacitor banks, like in big VFDs or power supplies, there are specific safety procedures, even in codes like the Canadian Electrical Code.
Absolutely critical. Large capacitor banks store a lot of energy. Even after you turn the main power off, they can hold a lethal charge for a significant time.
So you have to discharge them safely before touching anything.
Yes, usually involves specific procedures using discharge resistors or shorting bars following lockout-tagout. Treat them like a loaded battery that can discharge very quickly.
Okay, we've built a solid foundation. Now we can finally step into the world of solid state with the component that really started it all, the diode.
Right. And diodes are made from semiconductors. The classic one is silicon, which has 4 valence electrons in its outer shell.
Kind of sits between conductors like copper with few valence electrons and insulators with many.
Exactly. It's not great at either job on its own, so we dope it. We add tiny amounts of impurities.
To create N-type and P-type material, what's the difference?
N-type is doped with an element that has 5 valence electrons. This leaves extra loosely bound electrons floating around. These free electrons are the main current carriers.
Negative charge carriers, hence type.
You got it. P-type is doped with an element having only 3 valence electrons. This creates holes places where an electron should be but isn't. These holes act like positive charge carriers.
Positive P-type. Makes sense. And when you pick a piece of N-type next to a piece of P-type,
You create a PN junction. And that single junction is the fundamental electronic device we call a diode. Think of it as a one-way street for current.
okay, one-way street. Which way?
Current flows easily only from the anode side, the P-type, to the cathode side, the N-type. To get it flowing, you need to forward bias it.
Meaning the anode needs to be positive relative to the cathode.
Correct. But there's a catch. It's not like a perfect switch. There's a small voltage barrier at the junction you have to overcome first.
Ah, the barrier potential.
Exactly. For a standard silicon diode, you need to apply about 0.7 volts in the forward direction before it really starts conducting significant current. Below that, very little happens.
So there's always that small voltage drop across a conducting diode.
Always. Around 0.7 volts for silicon.
And if you try to push current the other way, cathode positive relative to anode.
That's reverse bias. The diode basically shuts off. It acts like an open switch with very high resistance, blocking current flow.
Okay, so forward bias, F on, with a 0.7 V drop. Reverse bias equals OFF. That brings us to ratings. What are the absolute key specs for a diode?
Two main ones you absolutely need to pay attention to, especially in power circuits. First is IFAVV, the maximum average forward current it can handle continuously without overheating.
And the second, arguably even more critical for survival.
VIF-AVE, the repetitive reverse maximum voltage, sometimes called peak inverse voltage, PIV, or peak reverse voltage, PRV. This is the absolute maximum reverse voltage the diode can withstand without breaking down.
Exceed VIF-AV.
Poof! The diode fails, usually shorted. It loses its blocking ability.
And this VIF-AV is where our AC theory from earlier becomes super practical.
Yeah.
Let's revisit that rectifier calculation.
Right. If you want to rectify, say, a 240-volt AC line, remember that 240V is the RMS value.
The peak voltage is higher.
Much higher. It's $240 text volts times squarter, which is about 339.4 volts.
So during the part of the AC cycle where the diode is supposed to be blocking reverse bias, it sees that peak reverse voltage.
Exactly. So your diode's VIRM rating must be greater than that peak voltage, so greater than roughly 340 volts to survive. In practice, you'd choose something significantly higher for a safety margin, maybe 600V or 1000V rated diodes.
Wow. Okay, so the RMS voltage directly dictates the minimum reverse voltage rating needed.
Absolutely. And that VRM requirement, along with a forward current for rating, largely determines the physical size and construction of the diode.
Because handling higher voltage and especially higher current means generating more heat.
A lot more heat. Remember, 2R losses, even with that small 0.7V forward drop, if you have hundreds of amps flowing, that's significant power dissipation. P equals VI. That's why high current diodes are physically large, often stud-mounted or hockey puck style.
And they need those big aluminum heat sinks.
Mandatory, often with thermal compound to ensure good heat transfer and sometimes even specific clamping pressures for the puck-style diodes to make proper thermal contact with the heatsink. Heat is the enemy.
It's total sense. Okay, let's quickly wrap up with the common jobs these diodes do. The obvious one first, rectifier diode.
Primary function, convert AC to pulsating DC. The one-way street in action.
Next, the freewheeling diode. This one's crucial for protecting circuits with coils.
Yeah, you connect it backwards or in parallel with a DC inductive load, like a relay coil or solenoid. When you turn the coil off, that CEMF spike we talked about tries to happen. But the freewheeling diode provides an easy path for the coil current to circulate and decay safely, instead of arcing across the switch. It clamps the voltage spike.
Very clever. Then the blocking diode, or isolating diode.
Think of preventing reverse current flow, like stopping a battery from discharging back into a charging source if the source fails, or preventing parallel power supplies from backfeeding each other. Simple but effective isolation.
And finally, the steering diode.
You often see these in logic circuits or AC control schemes. For example, you might use diodes to direct the positive half cycle of an AC signal to one part of a circuit, like an on coil, and the negative half cycle to another part, like an off coil, steering the current based on polarity.
Got it. 4 key roles stemming from that basic one-way action.
Pretty much sums it up.
Okay, what a tour. We really covered the ground from the language of electricity itself, RMS versus peak, so critical through the components R, C, and L that shape energy flow and phase, and landed squarely on the diode, the gateway to solid-state power control.
Yeah, and it all really hinges on understanding that controlled one-way flow that the diode provides. But, respecting its limits, that 0.7-volt forward drop is a cost. And exceeding the reverse voltage of VRM is fatal to the component. Get those, and you can start making sense of almost any power electronic circuit.
Right. We found out that just to handle a standard 240-volt AC line safely, a rectifier diode needs a VRM reading over 339 volts, purely because of the peak nature of AC. So, here's something to think about next time you're looking inside a piece of industrial equipment. Knowing that this reverse voltage requirement, coupled with the current it needs to handle, directly dictates how big that diode is, how big its heatsink needs to be, maybe even how it's physically clamped in place. How does understanding that fundamental VRM calculation change how you perceive, say, a really chunky bolt-down stud diode? Does it look less like just a component and more like a carefully engineered solution to a specific voltage challenge?